Electric field definition. First of all, I am talking about a point charge. Till now, we are talking about a point charge. So we have a point charge. I give an example. Any point, any charged object, we can say Q, can create or must create an electric field at any point in the medium. For example, if I take a point A and a point B, A is at a distance RA, and B is at a distance RB. This is RA and this is RB. So this charge must create at this point and this point and any point an electric field. The direction of this electric field, depends on the sign of this charge. If this charge is positive, so the field must be out. So here we have EA in the case if Q is positive, and if Q is negative, the field must be in this direction, EA in this direction in the case if Q is negative. So in and out depends on Q. The same for B. B, we can say here's a field as a point B. It must be in or out, depends on the value of Q. I am talking here in the general case, EB, it's in if Q is negative, and EB is out in the case of Q is positive. It's a general case. Now I will take a special case. I give a positive charge Q, a point charge Q. I repeat, it's a point charge Q, and we have a point A, and this object has Q1 as charge. So at A, we must have a field as Q1 is positive, so EA must be directed outward. So at this point, EA is out. This is EA. If I take another negative charge Q2 or positive, it depends, or any value, we can say Q2, and I put Q2 at the position A. Before, I want to tell you something. So before putting this charge, to have an electric field, you don't need two charges. One charge, it's enough to create an electric field in the medium. It's important, this point. To have an electric field, only one charge is enough to create this field. Now I put another charge Q2. When we have two charges Q1 and Q2, so these two charges will create an electric force between them. You know, if these two charges are identical, we will get a repulsive force. If these two forces are opposite, so we will get a, here we have an electric force, here we have an electric force. It's out and in, repulsive and attractive. It depends the sign of this one. So I put here a charge. We can say if this charge, if Q2 is positive, charge, yani we put here a positive charge, so Fe F12 must be outward, must be out. So in this case, F1, 2 out, it means in this direction. Alors, we have this one. We have F1, 2. If Q2 is positive, and here we can get F1, 2 in the case of Q2 is negative. So if Q2 is positive, EA and the electric force F12 have the same direction. If Q2 is negative, so F12 and EA have an opposite direction. So if Q2 is positive, we can say F12 and EA and has same or have same direction. If Q2 is negative, F12 and EA have opposite direction. It's important, this one. Now, you know the relation of E. For example, I do it. It's a positive of any charge at this point. If we have this one, Q1, I want to find the field here. Here we have EA. EA, if this positive, for example, it must be out. The field at this point equal, we can take the magnitude value. I am talking about the magnitude value. EA equal K. We have only one charge. Here we have nothing. It's a position. Equal KE, absolute value of the charge divided by the distance between square. This is the distance. Okay, this is the value of the absolute value. In the case, if we put here a charge, a positive charge, it's positive, so EA and FE have the same direction. It's F, we can say FE. Also, as magnitude, you know Fe equal by Coulomb's law equal Ke Q1 Q2 divided by the distance square. It's important to know these two equations and the relation between them. So EA equal key R2 key1. Okay, finally, you know the relation between these two equations. FE equal Q times E. Q is this one, is this one. This is the relation between these two, between the electric field and the electric force. Remember, if Q is positive, FE and E same direction. Same. I don't want to repeat. If Q is negative, FE and E has opposite direction. Here we have the equations. FE equal, don't forget its absolute value here, equal Q1 Q2 over R square, and this is the relation between E and F. E equal F over Q equal KQ over R square. And about the direction, it depends. We can put I and J. It depends the problem. Now, in the case, if we have a multiple charges, many charges. For example, here we have a, we can say here we have a positive charge, here we have a negative charge, here we have a positive charge, Q1, Q2, Q3. Every charge must create an electric field at any point. We can take an example, this point. If you want to find the total field applied on this point A, I have to join every point here, like this. It's important. We can begin with 1, Q1. So it's positive, so EA must be out. And Q2, we can join like this. We can take another color. Q2 like this. Q2 is negative, so it must be in. And we have Q3. We join these 2 points. So Q3 is positive, it must be out. Here it must be out. So here you have E A by the effect of the charge 1. Here you have E A by the effect of the charge 3. And here you have EA by the effect of the charge E2. And if I need to calculate the total field, you have to do the projection on the x-axis and y-axis. For example, here you can take, oops, okay, here you have y-axis, here you have x-axis, and you can calculate the projection of each vector on the x-axis and y-axis. Okay, you can say the E total on the point A equal EA1 plus EA2 plus EA3. And after you do the projection on each, you can calculate the components. Okay, you can solve a problem like this later.